What if the mysterious object racing through our solar system isn't what it appears to be? Fresh observations of 3I/Atlas are revealing characteristics so unusual that some scientists are questioning whether we're dealing with a natural comet at all. This interstellar visitor's trajectory, timing, and behavior patterns are defying conventional explanations, leading to heated debates in the scientific community. Today, we'll examine the mounting evidence that suggests this cosmic wanderer might be far more extraordinary than anyone initially imagined, and explore the controversial possibility that we could be witnessing something truly unprecedented. Discovery and initial detection. The story of 3I/Atlas begins with a routine sky survey that would soon turn extraordinary. On July 1, 2025, the Atlas telescope system at Rio Hurtado Observatory in Chile captured images of an unusual fast-moving object designated A11PL3Z. Larry Deneau from the University of Hawaii's Institute for Astronomy immediately recognized that this wasn't an ordinary solar system object. Within days, follow-up observations confirmed what astronomers had suspected. This was the third confirmed interstellar visitor in human history, joining the ranks of 1I Oumuamua discovered in 2017 and 2I Borisov found in 2019. The object received multiple designations, 3I Atlas for its interstellar status, and C2025N1 for its cometary characteristics. What made this discovery particularly intriguing was that despite entering our solar system weeks earlier, 3I Atlas had remained undetected due to its challenging viewing angle against the dense star fields near Sagittarius. John Tonry, principal investigator of the Atlas project, noted that pre-discovery images dating back to June 14, 2025 revealed the object had been silently approaching our solar system for an extended period. This late detection would prove to be just the first of many unusual characteristics that would set 3I Atlas apart from any cosmic visitor we'd ever encountered. Extraordinary orbital characteristics. Prepare to have your mind blown by the absolutely extraordinary orbital mechanics of this interstellar wanderer. Davide Farnocchia from NASA's Jet Propulsion Laboratory has calculated that 3I Atlas follows a hyperbolic orbit with an extreme eccentricity of 6.14, the highest value ever recorded for any known interstellar object. This mathematical measurement indicates just how dramatically different this visitor's path is from anything bound to our solar system. Even more remarkable is its incoming velocity of 58 kilometers per second, making it the fastest interstellar visitor ever recorded approaching our cosmic neighborhood. But here's where things get truly suspicious. The trajectory lies almost perfectly within the ecliptic plane, the flat disk where most planets orbit the Sun. Marco Micheli from the European Space Agency has calculated that the probability of this alignment occurring by random chance is merely 0.2%. This isn't just unusual, it's astronomically improbable. Most objects from interstellar space would approach from random angles, yet 3I Atlas chose a path that seems almost deliberately designed for optimal planetary encounters. The precision of this trajectory has prompted some researchers to question whether we're witnessing natural celestial mechanics or something far more intentional. Such mathematical precision in cosmic trajectories typically requires either extraordinary coincidence or deliberate planning. Suspicious planetary encounters. The planetary encounter sequence of 3I Atlas reads like a carefully choreographed cosmic ballet that defies statistical probability. Robert Warwick from the University of Western Ontario, who previously discovered Oumuamua, has analyzed the object's path and found it passes unusually close to Venus, Mars, and Jupiter during its solar system transit. The probability of such close encounters occurring randomly has been calculated at an astounding 0.005%. Essentially impossible by chance alone. But the timing gets even more suspicious. Paul Chodas from NASA's Center for Near-Earth Object Studies has determined that 3I Atlas reaches its closest approach to the Sun precisely when Earth would be positioned on the opposite side, blocking direct observation during the most critical phase of its visit. The statistical probability of this alignment? A mere 7% chance. Karen Meach from the University of Hawaii has noted that rather than resembling the chaotic path of a randomly ejected comet, the trajectory appears optimized for studying the inner solar system planets while minimizing detection risks. This orbital choreography provides optimal vantage points for comprehensive planetary observations, exactly what you'd expect from a reconnaissance mission rather than a chance cosmic encounter. The mathematical precision required for such a trajectory suggests either unprecedented natural coincidence or deliberate design by an intelligence capable of interplanetary navigation. Physical properties and anomalies. The physical characteristics of 3I/Atlas are equally perplexing and honestly challenge our understanding of typical interstellar objects. Daryl Seligman from Michigan State University has determined that the object measures somewhere between 1 to 12 kilometers in diameter, making it significantly larger than both previous interstellar visitors and providing an unprecedented opportunity for detailed study. Spectroscopic analysis suggests this cosmic wanderer is extraordinarily ancient, potentially 7 billion years old, predating our entire solar system by billions of years. This makes it a genuine cosmic fossil, carrying secrets from the early epochs of our galaxy. Quanzi Ye from the University of Maryland has confirmed that 3I/Atlas is the brightest interstellar object ever observed, allowing for detailed spectroscopic analysis that just wasn't possible with previous visitors. Perhaps most intriguingly, the object exhibits a 29-hour rotation period with minimal brightness variation, suggesting either a spherical shape or a uniform surface composition, characteristics that are pretty unusual for natural comets. Matthew Knight from the Naval Research Laboratory has noted that high-resolution observations reveal a remarkably compact and dense appearance, lacking the typical fuzzy, diffuse structure expected from ancient comets. These physical properties suggest either an unusually well-preserved natural object or something with a fundamentally different composition and structure than anything we've previously encountered in our solar system. Comet-like features versus anomalous behavior. Here's where 3I/Atlas becomes truly enigmatic. It displays some comet-like characteristics while simultaneously exhibiting behavior that frankly just defies cometary physics. Alan Fitzsimmons from Queen's University Belfast has confirmed that the object shows a faint coma and a short tail measuring approximately 3 arc-seconds, indicating active outgassing as solar radiation heats its surface. Spectroscopic observations have detected the characteristic signature of sublimating water ice, producing the dust and gas envelope typical of approaching comets. However, Tony Farnham from the University of Maryland has noted several anomalies that challenge this interpretation. Despite its proximity to the Sun and evidence of outgassing, 3I/Atlas maintains a remarkably compact, dense appearance that differs dramatically from the fuzzy, diffuse structure of typical comets. Most puzzling is the absence of an expected extended tail, which really should be prominent given the object's size and solar distance. Bin Yang from the European Southern Observatory has observed that the outgassing patterns don't follow standard cometary models, with irregular brightness variations that suggest complex subsurface processes. The combination of active sublimation with maintained structural integrity presents a paradox. How can an object simultaneously behave like a comet while retaining characteristics more consistent with a solid engineered structure? This contradiction has sparked intense debate about whether we're observing natural cometary processes or something fundamentally different masquerading as a comet. Scientific debate: natural versus artificial. The scientific community has erupted into heated debate over the true nature of 3I/Atlas, with interpretations ranging from exotic natural phenomena to, well, potentially artificial origins. Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard University, has emerged as the most vocal proponent of considering artificial origins, pointing to the statistically improbable trajectory and suspicious timing as evidence that, in his view, warrants serious investigation. Loeb argues that the mathematical precision of the object's path, combined with its optimal positioning for planetary reconnaissance, exceeds reasonable expectations for random cosmic events. His Galileo project at Harvard has been mobilized to conduct systematic observations using multiple telescopes worldwide. However, mainstream astronomers have pushed back strongly against these suggestions. Sarah Seeger from MIT acknowledges the unusual characteristics while emphasizing the importance of exhausting natural explanations before considering extraordinary possibilities. Robert Yedecke from the University of Hawaii has criticized speculation about artificial origins as premature and potentially damaging to scientific credibility. The debate highlights fundamental questions about how we interpret anomalous data and the threshold of evidence required for paradigm-shifting discoveries. Alan Stern, principal investigator of the New Horizons mission, has noted that while the characteristics are unusual, the universe is full of phenomena that initially appear impossible until we develop a better understanding of the underlying physics. Spectral analysis mysteries. The spectroscopic data from 3Y Atlas is revealing some puzzling inconsistencies that are, honestly, challenging our understanding of interstellar object composition. Stephanie Malam from NASA Goddard Space Flight Center has been coordinating observations using the James Webb Space Telescope to conduct detailed infrared spectroscopy of the object's composition. Initial results confirm the presence of water-ice spectrum, but the patterns just don't match our expected models. Jacqueline Keene from Boston University has identified these anomalous spectral signatures, where the observed signals actually increase in regions where water-ice models predict they should decrease. This contradiction suggests either unknown compositional elements or maybe structural properties that don't conform to standard cometary models. Now the object exhibits a distinctly reddish coloration, similar to objects in our outer asteroid belt, yet its interstellar origin kind of rules out formation in our solar system. Michelle Bannister from the University of Canterbury has noted that attempts to determine precise composition are complicated by the active coma surrounding the nucleus, which creates interference in spectral measurements. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory has suggested that these unusual spectral characteristics might indicate exotic ice compositions or internal structures not found in solar system objects. So, these spectroscopic mysteries really add another layer of intrigue to an already enigmatic visitor, suggesting that 3I Atlas may be composed of materials or structured in ways we just don't yet understand. Dark forest hypothesis implications. The behavior patterns of 3I Atlas align remarkably well with theoretical models of how an advanced civilization might conduct reconnaissance while avoiding detection. The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin, suggests that intelligent civilizations remain hidden to avoid potential threats from other species. Seth Shostak from the SETI Institute has noted that 3Y Atlas exhibits what could be interpreted as stealth-like behavior, deliberately timing its closest solar approach when Earth would be positioned to block optimal observation. This timing ensures that the most detailed study phase occurs when our planet's scientific instruments have limited access to the visitor. Jill Tarter, former director of SETI research, has observed that the trajectory allows for comprehensive surveying of inner solar system planets, while minimizing exposure to potential detection by any resident intelligence. The orbital path provides optimal vantage points for studying Earth's atmosphere, Mars's surface conditions, and Venus's cloud dynamics, exactly the type of data an exploring civilization would prioritize. Frank Drake, creator of the famous Drake equation, noted before his passing that such reconnaissance patterns would represent logical exploration strategies for risk-averse civilizations. While most scientists remain skeptical of artificial explanations, the behavioral patterns of 3I Atlas do match theoretical models of how cautious interstellar explorers might operate when encountering potentially inhabited star systems. Historical context and lessons. The discovery of 3I Atlas comes with profound lessons learned from our missed opportunities with previous interstellar visitors. When 1I Oumuamua was discovered in 2017, the scientific community was caught completely unprepared for studying such a rare phenomenon. Robert Warwick, who discovered Oumuamua using the Pan-STARRS 1 telescope, has reflected on how the object's rapid departure left many critical questions unanswered. The mysterious acceleration exhibited by Oumuamua without visible outgassing remains unexplained to this day, highlighting the importance of comprehensive observation campaigns. Gennady Borisov, the amateur astronomer who discovered 2I Borisov in 2019 from his observatory in Crimea, provided the astronomical community with a second chance that was better utilized. However, even Borisov's study was limited by available technology and coordination protocols. Mark Norris, from the University of Central Lancashire, has emphasized that 3I Atlas represents our most comprehensive opportunity yet to properly study an interstellar visitor with advanced instruments and coordinated global observation campaigns. The improved detection capabilities of modern sky surveys, combined with rapid communication networks, have enabled real-time coordination among observatories worldwide. Michelle Bannister has noted that the lessons learned from previous interstellar encounters have fundamentally changed how the astronomical community approaches these rare events, ensuring that we're better prepared to unlock the secrets these cosmic messengers carry from distant star systems. Future observations and implications. The coming months represent a critical window for determining the true nature of 3I Atlas before it departs our solar system forever. Perihelion is scheduled for October 30th, 2025, after which the object will begin its journey back toward interstellar space. Paul Chodas has calculated that 3Y Atlas will re-emerge from behind the Sun in December 2025, providing a final opportunity for detailed observations before it becomes too distant for meaningful study. Karen Meach is coordinating an unprecedented international observation campaign involving over 50 professional observatories and numerous space-based instruments. The Hubble Space Telescope, James Webb Space Telescope, and ground-based facilities including the Very Large Telescope in Chile are all dedicating precious observation time to this cosmic visitor. Daryl Seligman has noted that the data collected during this campaign will either confirm 3I Atlas as an exotic but natural interstellar comet, or potentially revolutionize our understanding of what's possible in our cosmic neighborhood. The implications extend far beyond pure astronomy. If 3I Atlas proves to be artificial, it would fundamentally alter humanity's perspective on our place in the universe and our approaches to planetary defense and interstellar communication. Alan Fitzsimmons emphasizes that regardless of the final interpretation, 3I Atlas represents a pivotal moment in astronomy, where advanced technology meets unprecedented opportunity to study materials and possibly intelligence from beyond our solar system. As 3I Atlas continues its mysterious journey through our solar system, it challenges everything we thought we knew about interstellar visitors. Whether this ancient wanderer is an exotic natural phenomenon or something far more extraordinary, it's forcing us to expand our understanding of what's possible in the cosmos. The next few months will be crucial in determining the truth about this enigmatic visitor before it disappears back into the depths of space. Stay tuned to InnoVision Tech for the latest updates on this cosmic mystery. Like, share, and subscribe. A cosmic object 100 times bigger than anything we've ever tracked just entered our solar system, and it looks like it's hunting a smaller, equally strange visitor that arrived just weeks before. On September 12, 2025, astronomers witnessed an impossibility. Two massive, anomalous bodies arriving from opposite ends of the galaxy, set to rendezvous near the Sun. The odds are non-existent, and the evidence points not to a comet, but to a fortress. Let's explore this together. The Swan's dramatic arrival. What does it look like when the impossible streaks across the sky? On September 12, 2025, we found out. The SWAN instrument, a solar wind anisotropy sensor aboard the SOHO spacecraft, flagged a new object blazing a path through the inner solar system. The first data sets, analyzed by teams led by SOHO project scientist Bernhard Fleck, were staggering. The object possessed a tail stretching nearly 2.5 degrees across the sky, about 5 times the width of a full moon. To put that in perspective, a tail of that magnitude suggests a hydrogen outgassing rate hundreds of times greater than a typical long-period comet. Its initial brightness was clocked at magnitude 7.4, luminous enough to be seen with backyard telescopes from a distance of over 150 million kilometers. This wasn't some faint smudge. This was a spectacle. News ignited across astronomy networks, and just 2 days later an amateur observer captured a jaw-dropping image showing a streak so immense it barely fit the camera's frame. It was too big, too bright, and its trajectory was already looking far too precise. The raw energy output required to generate such a visible display at that distance was the first red flag that this was something entirely new. Official recognition and growing mystery. How do you classify something that breaks all the rules? By September 13th, the Minor Planet Center, where figures like the late, great Gareth V. Williams once vetted such discoveries, made it official. The object was designated C/2025 R2 or SWAN, acknowledging the instrument that found it. That official stamp kicked off a global frenzy. Its initial orbital eccentricity was calculated at over 0.999, confirming it as a long-period visitor on a path that would take millennia to repeat. The sheer size and luminosity created a wave of disbelief. Veteran astronomers had to reach back to the legendary comet Hale-Bopp of 1997, a comet with a nucleus estimated at 60 kilometers in diameter, to find a worthy comparison. Swan, however, was already outshining Hale-Bopp at a similar distance from the Sun. It was slicing through the constellation Virgo, growing brighter as it approached its perihelion of roughly 1.0 astronomical units, the same distance as Earth is from the Sun. The question shifted from what it was, to why it had arrived right now with such perfect timing. The numbers didn't just suggest a large object, they hinted at an impossibly active one. The cosmic coincidence. Some things are so unlikely, they stop looking like a coincidence. C/2025. R2 Swan is not the only strange visitor this October. Days before, another object, 3I/Atlas, was already inbound from a completely different part of the sky. Imagine a celestial map. Swan's path traces back from Aquarius, while Atlas entered from the direction of Sagittarius. Yet, both are set to reach their closest pass by the Sun within the same 10-day window. For Atlas, that's October 17th at a distance of 1.36 astronomical units. For Swan, it's just 3 days later, around October 20th, at a much closer 1.0 astronomical units. Their perihelion points are separated by only about 50 million kilometers, closer than Mars ever gets to Earth. The geometry is what's truly stunning. Both are on steeply inclined orbits, with Swan's path tilted more than 60 degrees and Atlas nearly 90 degrees to the ecliptic plane. As orbital dynamicist Paul Wiegert would tell you, the statistical probability of this kind of synchronized arrival from such different trajectories is infinitesimally small. It's a corridor in space-time that seems to have been deliberately targeted. This is not random chance, it is a rendezvous. Atlas breaks the rules. So what do you do when an object's very existence kind of violates physics? 3I/Atlas, discovered by the University of Hawaii's Asteroid Terrestrial Impact Last Alert System Survey, which was headed by Larry Deneau, first got attention for its composition. Early spectrographs showed a body dominated by nickel, with almost no iron at all. This, honestly, directly contradicts our knowledge of asteroids, which nearly always feature iron-nickel alloys in, pretty predictable ratios, but the anomalies didn't stop there. Instead of water vapor, Atlas's coma was surprisingly pumping out carbon dioxide, with its 4.3 micron spectral line dominating every reading. But the real smoking gun was its movement. Observers logged 3 distinct non-gravitational accelerations, on July 29th, August 14th, and August 30th. These weren't smooth pushes, they were sharp bursts, delivering a delta V of several meters per second each time. The behavior was so precise it was dubbed thrust mix modulation, which, honestly, implies a controlled engine burn that was adjusting its composition output. The data held up across multiple observatories, painting a pretty clear picture. This thing was under its own power and, yeah, on a mission. The physics just honestly left no other room for interpretation. Swan, the fortress. If Atlas is a nimble drone, then Swan is, well, a battleship. The scale of C/2025 R2 is hard to even comprehend, but honestly it's the data that paints a pretty radical picture. One that has driven speculators like Harvard's Avi Loeb to consider similar theories for other objects. It all began with reflectance data. Swan's core has an albedo, or reflectivity, that's far higher than a typical dark comet nucleus, actually matching the signature of polished metal. Some analysts argue it fits a nickel-cobalt blend, which is an alloy used for its immense strength. Then, reports started coming in about a silvery halo around the nucleus, an anomaly some interpret as a plasma envelope or maybe even an electromagnetic shield. This is where it earned the nickname the Fortress. Unlike Atlas, Swan appears steady and honestly invulnerable, refusing to fragment as it nears the Sun. Even its tail shows evidence of microthrusts, tiny rhythmic pulses at a consistent frequency that, frankly, defy natural outgassing. Add in its 22,554-year orbit, and you have an object that appears to be ancient, armored, and well, on a deliberate, powered course. It isn't just passing through, it's arriving. Mission theories. When a 1 in a trillion coincidence happens, you kind of have to consider it wasn't a coincidence at all. The timing, the geometry, and all this anomalous behavior have really fueled mission theories. One is a scheduled refueling run, an idea that actually fits with concepts of advanced astroengineering proposed by physicists like Freeman Dyson. A more unsettling theory is, well, an intervention. a rendezvous to neutralize a malfunctioning unit. The estimated power levels, Atlas at 10 gigawatts and Swan at a staggering 10,000 gigawatts, suggest energy reserves needed for active maneuvering, not just passive drifting. There's also the audit chain scenario that 1I/Oumuamua in 2017 and 2I/Borisov in 2019, both on hyperbolic trajectories, were scouts. Atlas was a more advanced follow-up, and now Swan is the main event. In every case, the sun is the rendezvous point, the most powerful energy source in the system. The evidence really forces us to ask, if this is a mission, what is the objective? These aren't just rocks, they're actors on a cosmic stage. Ancient connections. An orbit of 22,554 years is, a link to a different chapter of human history. The last time Swan would have passed was around 20,000 BCE, right at the peak of the last glacial maximum. This is where the story connects to Göbekli Tepe, a site in Turkey built around 9500 BCE. Researcher Martin Sweatman has proposed a controversial theory that its pillars are an astronomical observatory, recording a cataclysmic comet impact that triggered the Younger Dryas climate shift. He argues that Pillar 43 specifically tracks a long-period celestial object. Mainstream archaeologists, including the site's original lead excavator Klaus Schmidt, have strongly disputed this, maintaining the carvings are symbolic. Still, the timing is, hard to ignore. If Swan is on a recurring path, its last visit coincided with a transformative period for humanity. Whether that is a coincidence or a clue remains a fiercely debated question. It adds a layer of mythic resonance to an unbelievable event, suggesting we may have seen this visitor before. The blackout window. Just when things are about to get interesting, the curtains are being drawn. From October 8th to 18th, every major ground-based observatory from the Very Large Telescope in Chile to the Keck Observatory in Hawaii is effectively blind. This solar conjunction is predictable. What isn't normal is the alleged response. According to inside sources, memos from US Space Command and the ESA have directed teams to suspend all imaging. The official rationale is to protect sensitive optics from the sun's glare. But that doesn't explain why radar facilities like Arecibo's successor, which are immune to solar glare, would also be ordered to stand down. This specific detail makes the official story fall apart. Proposals for alternative observation methods have reportedly been denied, and data requests have been delayed. Several telescope allocation reviewers describe explicit orders to avoid public statements. The result is a forced information vacuum at the most critical moment. Underground resistance. When the official channels go dark, the people build their own. The blackout order may have silenced major observatories, but it ignited a firestorm in the amateur and independent astronomy communities. Veteran tracker Bill Gray put out a call to arms across public forums: keep your scopes on the sky, log everything, and share the raw data on open-source servers. A distributed web of astronomers with powerful 14 and 20-inch telescopes answered. Collectives like the Ibero Tracker Group in Europe began pooling their photometric and astrometric data feeds. Leaks suggest plans to use radio telescopes to pierce the solar glare. This grassroots effort has become the only real-time source for what might happen during the blackout. It's a powerful narrative of decentralized science, a global network ensuring no data disappears. When Swan and Atlas re-emerge, the first images confirming their post-perihelion behavior might come from a garage, not a government lab. This has become a testament to citizen science. Power estimates and implications. Let's talk about the energy required to make these objects move. Atlas's accelerations required a power source of around 10 gigawatts, the output of 10 large nuclear power plants, but that is dwarfed by Swan. Based on its luminosity, its suspected micro-thrusts, and the energy needed for a plasma shield, the Fortress could be wielding something close to 10,000 gigawatts. That is more raw output than the entire power grid of planet Earth combined. On the Kardashev scale, a civilization capable of controlling energy on this level is approaching Type 1 status. These are not trivial anomalies. These figures are the hardest evidence to dismiss as natural phenomena. They move the conversation from astronomy into astroengineering and contact theory. The sheer physics involves screams that we are dealing with a technology far beyond our own, powered by a source we can't yet comprehend. This is the bottom line that makes the engineered object hypothesis so compellingly logical. The facts are as clear as they are unnerving. Two anomalous objects defying all statistical odds have entered our solar system on a synchronized path. One appears to be a powered drone, the other an armored fortress. They are scheduled for a close encounter during a 10-day window where they will be conveniently hidden from our best telescopes by the sun, accompanied by an official top-down order for radio silence. This has forced the search for answers into the hands of a global network of citizen scientists. Are we witnessing a cosmic accident, a pre-planned mission, or something else entirely? Whatever the truth is, we are about to find out. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech. What if our first clear chance to photograph an interstellar visitor was deliberately sabotaged? On October 7, 2025, the world held its breath for a portrait of the interstellar Comet 3 I/Atlas as it flew past Mars. Instead, we got a blurry dot, a global controversy, and a coordinated silence from the world's leading space agencies. This wasn't just a technical glitch, it was the start of a mystery that points to something being hidden in plain sight. Let's delve into it. The blurry dot. It was supposed to be the space photo of the decade, but it looked like a mistake. At precisely 9:22 UTC on October 7, 2025, the European Space Agency released the first official image of 3 I/Atlas, captured by the CASIS camera on the ExoMars Trace Gas Orbiter. The public expected the stunning high-resolution detail we've come to associate with our Martian probes. What they received was a single, fuzzy, underwhelming pixel against the blackness of space. The comet, with an apparent magnitude of +19, was incredibly faint. Within an hour, this blurry dot became a global phenomenon for all the wrong reasons. The team behind the camera, led by its principal investigator, Nicholas Thomas, from the University of Bern, knew they were pushing their instrument to its absolute limits. CASIS was designed to look down at Mars from an altitude of 400 kilometers, not out into the deep void. They had performed a complex slew maneuver, pointing the entire 4,332-kilogram spacecraft at a target 30 million kilometers away that was over 10,000 times fainter than anything the camera was built for. The resulting image wasn't a failure, but a triumph of engineering that required stacking multiple exposures to even get a detection. The world, however, didn't see a technical miracle. It saw a smudge and immediately began asking what was being hidden from view. Global outrage. The internet doesn't wait for explanations, it demands answers. The moment the blurry dot hit social media, the backlash was instantaneous and brutal. Hashtags like fuzzy dot and where are the pics trended in over 20 countries, generating more than 1 million posts on X and Reddit within 24 hours. Side-by-side comparisons showing sharper images from backyard telescopes flooded every platform, fueling a narrative of incompetence, or worse, a deliberate cover-up. Renowned science journalists like Dennis Overby of the New York Times were forced to frame the story not around the science, but around the profound public disappointment. The outrage wasn't just about a low-quality photo, it was about the perceived breach of trust. After being spoiled by the crystal-clear images from the James Webb Space Telescope and the New Horizons Pluto flyby, this blurry dot felt like a step backward, an insult to the €1.7 billion price tag of the ExoMars mission. The simultaneous silence from NASA, China, and the UAE only poured gasoline on the fire. It created a dangerous vacuum of information that was quickly filled with suspicion, turning what should have been a scientific celebration into a full-blown public relations crisis. Technical limits. So, was this a cover-up, or just the hard reality of physics? The truth is, the blurry dot was inevitable, and the numbers prove it. Let me explain. The CASIS camera, developed by a Swiss-led consortium including scientist Gabriele Cremonese, is an imaging powerhouse when pointed at Mars. From its 400-kilometer orbit, it achieves a stunning resolution of 4.5 meters per pixel. But 3 I/Atlas was 30 million kilometers away. At that vast distance, the camera's angular resolution of 11.36 microradians per pixel translates to a pixel scale of about 340 kilometers wide. The comet's nucleus, the solid object at its core, was estimated by astronomers to be only about 15 kilometers across at most. This means the entire comet was just 4.4% of the width of a single pixel on the detector. It's like trying to photograph a single human being standing in San Francisco using a cell phone camera in New York City. No matter how perfect your focus, the light from that object will never fill more than 1 pixel. The fuzzy dot wasn't a blurry image of the comet, it was the entire image of the comet. Its faint light smeared across one single sensor element. It was a technical ceiling, not a conspiracy. The camera could only give a fingerprint, not a portrait.
High-rise goes dark.
If Europe's camera wasn't up to the task, surely America's best would deliver. All eyes turned to NASA's Mars Reconnaissance Orbiter and its legendary high-rise camera. This is the instrument that can resolve features as small as 30 centimeters on the Martian surface from its 255-kilometer orbit. Its power is, honestly, unparalleled. The team lead for HiRISE, planetary geologist Alfred McEwen of the University of Arizona, had plans to capture what would have been the most detailed image of an interstellar object in history. With its angular resolution of 1 microradian, HiRISE could have achieved a pixel scale of 30 kilometers at the comet's distance, good enough to put several pixels across the nucleus and reveal its shape. But just as 3I Atlas made its closest approach, HiRISE went dark. The official reason given was a US government shutdown that had begun on October 1, 2025, freezing all non-essential operations as part of the fiscal year 2026 budget impasse. Command uplinks to the orbiter were halted, data downloads were stopped. HiRISE team member Candace Hansen-Koharchek confirmed over 300 planned observations were lost, including the critical 3I Atlas sequence. While plausible, the timing felt incredibly convenient to a public prime for suspicion. The crown jewel of Martian imaging was sidelined at the most critical moment imaginable.
Radio silence.
NASA's silence was deafening, but they weren't the only ones who went quiet. 2 other powerful orbiters were perfectly positioned to observe 3I Atlas, China's Tianwen-1 and the United Arab Emirates' HOPE mission. Both had been tracking the comet on its approach. Tianwen-1 carries a high-resolution camera capable of imaging Mars at a resolution of 0.5 meters. The HOPE orbiter, managed by project director Omran Sharaf, has the Emirates Exploration Imager, or XI, a multi-band camera that could have provided crucial color data on the comet's coma. Yet in the days following the ESA image release, neither the CNSA nor the UAESA published a single frame of data. No press releases, no technical updates, not even a statement confirming they had attempted an observation. This coordinated silence from 3 independent space powers was, for many, the most damning piece of evidence. Experts in international space policy, like Professor Svetla Ben-Itzhak, have noted that while agencies often keep data proprietary, such a complete information blackout on a major public interest event is highly unusual. Why would 3 nations, often competitors in space, all simultaneously withhold their data? The lack of information felt less like a coincidence and more like an unspoken agreement.
The image wars.
When the professionals go quiet, the amateurs get loud. In the vacuum left by the silent space agencies, a global network of amateur astrophotographers began releasing their own images of 3I Atlas. These images, often the result of stacking dozens of 300-second exposures from 14-inch telescopes, appeared to show far more detail than the official ESA photo. Some claimed to see a distinct star-like core, a faint green tail, and even jets of gas erupting from the nucleus. The internet split into 2 camps. One side, championed by skilled imagers who produce work rivaling professional observatories, like Damian Peach, argued that citizen science was outperforming billion-dollar missions. The other side, composed of professional astronomers like David Jewett, warned that these details were likely illusions, or artifacts. They explained that techniques like aggressive sharpening and AI upscaling, which claim to boost resolution by 400%, can't create new information. They amplify digital noise and can turn random pixel fluctuations into false structures. The debate became a crash course in image processing, with terms like point spread function and signal-to-noise ratio trending on astronomy forums. Without official data as a baseline, the line between discovery and delusion had become, well, hopelessly blurred.
Perseverance streak.
While the world looked to the orbiters, the most intriguing clue may have come from the Martian surface. At the Jet Propulsion Laboratory, Justin Mackey, the imaging scientist for the Perseverance rover, authorized a unique observation. The rover's navigation camera, or NavCam, was pointed toward the constellation Ophiuchus for 10 minutes, taking a sequence of exposures as 3I Atlas was predicted to pass overhead. The raw frames revealed a single faint streak, just over a pixel wide, cutting diagonally across the image. The math was tantalizing. At its known speed of 90 kilometers per second, the comet would have traveled exactly 54,000 kilometers during that 10-minute window. A distance that perfectly matched the streak's angular length if it was the result of motion blur. It seemed like confirmation. But rover operations lead Vandy Verma later noted a catch. The same streak could be produced by a much closer object, perhaps a 10-centimeter piece of orbital debris from a past mission like Mars Global Surveyor, moving at just 7 kilometers per second over a shorter exposure. Without the full FITS data headers to confirm the exact exposure timing, the streak remained a 54,000-kilometer question mark, the first piece of hard but ambiguous data in a sea of speculation.
Wow signal link.
A blurry dot is one thing. A straight line to the most famous potential alien signal in history is another. As trajectory experts plotted the path of 3I Atlas through our solar system, they uncovered a coincidence that was just too stunning to ignore. The comet's path, when traced back, pointed to a location in the constellation Sagittarius, less than 2 degrees away from where, on August 15, 1977, astronomer Jerry R. Amon detected the legendary WOW signal. A powerful 72-second radio burst at 1420.4056 megahertz that has never been explained. Immediately, online forums lit up with calculations. For an object to produce a signal that's strong from its current distance, it would need a 2.2 gigawatt isotropic transmitter, the equivalent output of a large nuclear power station. The alignment was so perfect, so poetically resonant, that it felt like it had to mean something. Yet, inexplicably, major radio observatories like the SETI Institute, whose iconic scientist Jill Tarter has long advocated for such listening campaigns, announced no coordinated effort to listen for signals from the comet along the hydrogen line, the very frequency of the WOW signal. The silence was no longer just optical, it was now radio silence right when the stakes were highest.
Approaching perihelion.
The mystery is reaching its peak, yet the main character is about to leave the stage. On October 29th, the enigmatic object known as 3I Atlas will reach perihelion, its closest approach to the Sun. It will plunge to a blistering distance of just 0.3 astronomical units, well inside the orbit of Mercury. For the following 38.5 hours, it will be lost in the intense solar glare, a period astronomers refer to as a blackout. This impending information vacuum is allowing every theory, from the mundane to the extraordinary, to flourish. Some astronomers predict the object might completely disintegrate under the intense solar radiation which will heat its surface to over 400 degrees Celsius. But others, including those from Avi Loeb's Galileo project, wonder if this blackout could be used to hide something else, a deliberate maneuver. The Galileo project has put forth a compelling theory. An engineered course correction of even a few dozen meters per second, masked by the sun's gravity, would be definitive proof of an artificial origin. In anticipation of this, the project has announced a plan to use the Allen Telescope Array to listen for any telemetry pings the moment 3I Atlas is expected to re-emerge from behind the sun's limb. The world will have to wait. The approaching blackout is the ultimate cliffhanger in a story already short on answers.
The November tests.
The sun won't hide the truth forever. As 3I Atlas is expected to re-emerge into view in early November, a new phase of the investigation will begin. This will be a checklist of pass-fail tests for the object's authenticity. First, astronomers will work to build a detailed light curve, monitoring its brightness for any surges that could signal fragmentation. Second, its trajectory will be measured with extreme precision by the Minor Planet Center, which will look for any deviation from the predicted path not accounted for by natural outgassing. Meanwhile, another mission is waiting for its chance. The European Space Agency's JUICE spacecraft, currently on its way to Jupiter, is scheduled for an observation window between November 2nd and 25th. Its advanced instruments, including the Janus camera, promise a fresh look from a completely different angle, at a distance of about 0.4 astronomical units. Though JUICE will be farther from the comet than ESA's Mars orbiters were, it will have the advantage of observing 3I Atlas just after its closest approach to the Sun, when it is expected to be in a highly active state. However, due to the vast distances and anticipated low data transmission rates, the full dataset is not expected to reach Earth via ESA's deep space antennas until February 2026. For now, the mystery of 3I Atlas is set to continue. So, what is 3I Atlas? Is it a natural interstellar comet that arrived at the worst possible time, a victim of technical limits and bad timing, or is the blurry dot, the synchronized silence, and the impossible coincidence of the wow signal pointing to something more profound? The official story tells us of limitations, but the missing data tells a story of its own. We were given a front-row seat to one of the most significant astronomical events in human history, only to have the curtain drawn at the critical moment. The truth remains out there, hidden in the noise of a blurry image and the silence of the world's greatest observatories. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. Until next time, keep looking up InnoVision Tech.